Hi, today we are going to see breaking of column. Let's import our files. Import path. So let's start import the column with is individual and then deformable one. So let's import that and then let's import the part that we want as a plate. Okay. So while importing plate we won't need deformation for that. So let's consider as a discrete rigid and then import it. Okay. So after importing, let's create a reference point that we will need for the use. Okay, let's take a reference point of this and then let's continue. So now the property that we need actually, right? Okay, property for this I'm going to create. We have actually the bulking property that which need. So as we see, bulking has been given. So elasticity, and then we have given some plastic data that requires for it. Okay. So and then let's create thickness as a shell homogeneous. Let's create of thickness of three, and then okay, then assigning the thickness with actually selecting all these things and done, and then make it clear it's a mid surface. Okay, done. Then we have created thickness. Now let's go to plate. We need to create inertia. So let's take create inertia, point mass inertia. Let's take this and then we know inertia, and then let's done, and then we will give the inertia of 1.0, and then we'll go for it, right? And then we need to go for assembly. So let's import this assembly, both parts as independent, and then import it. Now what we are going to do is uh, we need one more plate at the top, right? So we are going to multiply it and then select this part, done. So it acts 0 and then take the direction of this, and then offset is for 5 1. Okay, so it's too high. So that will be good. So we can adjust those things and then while we are running. Okay, done. Now our this point of is done. So next step is we are going to create a step of dynamic analysis explicit. So continue, and then we are going to give a time period of 0.007 seconds. Go. Then we are going to edit the intervals for 30 because it will run more. Let's go for 40. It will help you out creating a less volume of your files, and then let's go tangential behavior, frictionless. It's tangential behavior. We know enough tangential behavior. We know enough. We'll go for normal behavior. That is okay. Done. And then we will create a general contact that we need in initial step. So creating a general contact itself and then property that we have created. And then now we are going to create a tie between these two parts. Let's create a tie. Okay, first constraint. Let's take this surface and then done, and then which is in purple in color, which is inside, and then select node region, and then let's take this region that we need. Down and then specify a distance of 0.001, so that will adjust itself. That will be good to go. And then same way we have to take the out other part kind of surface this. Then let's take brown, which is brown in color, and then node region, which is will be like this, not that. Let's rotate little bit for convenient, and then click this, and then take it done. So same specified of 0.001, that will be right good to go. And then now we have this two. Since we have going to take this as a rigid body, now we need to create a rigid body for it. Continue. So select the um, body. So this is the body done, and then reference point as this. Okay, right? That's a rigid body. And then let's take one more rigid body, which is the down. So body elements. So this done, and then let's take this is our first done. So now what we have created is body, and then let's go for loop conditions. So let's create initial, create this done. One, two, three, four, five, six. Go to. And then let's create one more at the initial, continue. And then we take this and then one, two. Let's go for five and six. Let's do these two be free. We are going to give velocity for it. So let's take step one. Okay, where's the velocity? And then let's take this RP done, and then we are going to do B3 as minus 50 done, and then again we are going to create one more velocity which is on different direction. So it is on minus 70. So go good to go now. Then let's go for mesh. Since both our things are independent, let's give some global value of let's take this will be okay, and then for this global done, that will take care soon. It will be good, so we can have a good output view, right? This and this done, and this done, and this done. And we have a very good, pretty good mesh. Now assign things for this and this. Continue as explicit, which is rigid, and then done. And then next is this. So done, explicit, linear, and then we have its shell. And okay, now the mesh is ready. And then now we are going to do the job. So let's create a job. Create model. Let's give buckling, continue, and then let's give parallelization of free, done, and then let's submit it out. So let's see the monitor, the how it actually behaves. See our analysis has been completed. Let's give dismiss and then see the results for the what we have created over here. And then let's look. Let's look. So okay, so we have a pretty good behavior of the buckling, which we will actually take only the elements of column. So replace and then go for it. And then let's queue. So it's pretty bit fast, and then we will actually reduce it out. Okay, okay. So, and then we can see it's pretty much in big numbers. Let's take it in small version. So, legend, make it fixed, apply okay, and then see the stress that we have attained for it. So, it's pretty bit too much. And then let's give for displacement, and then you can see, right, okay, it's behaving way different. So, with the help of a self context, we can see how it the features has been good to go. So if you're like this, and then you have can see by one step. So you can even have extraction of any like take a displacement of a U3 or for a particular node or a section that you want done, plot, and then you have the curve that you want, how it behaves. Even you can go for and stuff view, you can actually request for stress of one measure since it is a steel. So you can plot according to it. It will be like you can see it out or elastic strain of a maximum principle of the plot. You can see how it behaves. So it is a combination of stress and maximum principle. And if you don't want that, like you can um, take out that. So let's take have maximum principle for check the behaves plot. So you can see that how the maximum principle stress and things are going on. So so this is how to do it. Thank you.